Good morning and welcome everybody to another edition of the International Seminars Global Rivers in the Anthropocene, organized by the Graduate Program in Environmental Science, CIAMB, and LaboChef, Laboratory of Geography and Physical Geography and Geology of the Federal University of Goiás. And today we have a special guest. It's a big pleasure for me to introduce Professor Peng Gao, Professor and Chair of the Department of Geography and the Environment, Maxwell School of Citizenship and Public Affairs of Syracuse University in the United States. And it's a big pleasure because not just because Peng Gao is a remarkable scientist, but also because I consider myself, Peng Gao, to be my friend. So that's make this day very special for me. Professor Peng Gao is a physical geographer trained in fluvial geomorphology. His early research focused on the mechanics of sediment transport in artificial and natural rivers, as well as cascade hydrological and sediment movements through river watersheds. Since 2015, he has concentrated his research on the morphodynamics processes of natural rivers, meanderings, rider, and branchings in the Qinghai-Tibet Plateau of Western China. His research covered impact of climate change, glacier melting, and increased precipitation on wider river system in the source region of the Upper Yangtze River watershed in China, spatial and temporal alteration of peatlands in the source region of the Yellow River, also in China, mechanism of meandering rivers in response to the altered environmental changes because anthropogenic and climate drivers, and finally key fluvial processes controlling morphological change of branching rivers as well. Recently, Professor Peng Gao has been applying artificial intelligence concepts and techniques to identify spatially variable peatlands, depths, and areas of in the Qinghai-Tibet Plateau, and have been also exploring how urban morphology interact with microclimate, particularly through urban heat island and air pollution exposures to influence public health and the variable socioeconomic conditions. As well, on another front of geographical research, he demonstrated the temporal stability of geospatial patterns of gap violence in Syracuse and linked parameters characterizing 3D urban form to the intensity and distribution of urban heat islands. Professor Peng Gao also is a very active scientist that collaborates with several institutions in China. For example, Wuhan University, I was visiting recently, and also an active member of the Association of American Geographers. So please, Peng, welcome to our seminars. Go ahead, and we are here to listen and to learn with you.
Thank you, Edgardo, for your nice introduction. It's my pleasure to join this series of talk and to have a chance to introduce all of you my research relevant to rivers in the Qinghai-Tibet Plateau. And my talk, let me start my talk here. So the title of my talk is River Environment in the Qinghai-Tibet Plateau. And this is a talk basically reflecting on the research me and my Chinese colleagues have been doing in this area in the past 10 years. So I will walk you through the natural environment of this area and introduce you the results we have got in the past 10 years. And that in the end, I will reflect on what we learned from these areas regarding to the river systems on this unique plateau. Okay, now I want to start from the basic geographic introduction of the area. The Qinghai-Tibet Plateau is located in the western China, as you can see from this map. And this is the area, Qinghai-Tibet Plateau. And the area covers more than 2.5 million square kilometers. It's a huge, huge area. Most of the area is in China. Some of them is in other countries. And the mean elevation of the area is above 4,500 meters. So that is why Qinghai-Tibet Plateau is the world's highest plateau. And the plateau has the so-called highland monsoon climate, meaning it has a long cold winter and short warm summer with very high solar radiation. And this makes the area very harsh for human residents. And because of that, the population density is very sparse in the area. And from a geological perspective, the Qinghai-Tibet Plateau was formed about 50 million years ago. It was formed by the collision of two plates, the India plate and the Eurasia plate. India plate is essentially goes underneath of Eurasia plates. And this caused all kinds of so-called mountain build activities, and those kind of activities formed the geomorphological landforms we see today. So from a hydrological perspective, this geological activity formed the two kinds of basins called endorheic basin and the exorheic basin. As you can see from the left-hand figure, the blue color represents the exorheic basin, and this is the area where all the rivers were stopped in the so-called sink. The river will not come out from the area. The only way for water can get out of the endorheic basin is from evaporation. And the other area is called the exorheic basin, which is represented by this pink color. And in this area, water basically goes out of the system. It is this area that is today's focus. And in this area, the tectonic movement basically created a series of mountains running from northwest west to southeast and east in this kind of orientation. And as a result, the river systems created, as you can see from the right-hand side, right side pictures, is that the river systems basically follows this similar orientation. And specifically in the exorheic basin of Qinghai-Tibet Plateau, there are 5 big or large source river systems from north to the south. The first one is called the Upper Yellow River system. It is the source of Yellow River, which running through the China. The second one is called the Upper Yangtze River system, and this is the source area for the Yangtze River, which also running entirely through China. The third one is called the Lancang River, and this is a river upstream or source area of the rivers called the Mekong River. Some of you may have already read papers about this area. And the Mekong River passed through 4 Southeast countries, Laos, Thailand, Vietnam, and Cambodia. The 4th river system is called the Nu Jiang River, and this is a source area of the so-called Salween River, which runs through Burma. The last one, which is on the very south of the area, is called Yalongzangbu River or Yajiang River, and this is the source area of the Brahmaputra River that runs through India. So keep in mind that these are the 5 large river systems I'm going to talk about today. So next, before I get into each individual, I want to briefly show you some general characteristics of the 5 large river system. And the watershed area basically gives you the idea how large these areas are. And as you can see, Upper Yellow River, Upper Yangtze River, Upper Yajiang River are relatively large. The other 2 are relatively small. And the main channel length, the longest one is Yajiang River. And the main channel slope, the steepest one is actually Lancang River and the Yajiang River. I'm going to talk more about this. So water discharge sediment load is basically just give you the general idea regarding to the general status, like a discharge, like Yajiang River has the highest annual discharge and the water discharge, and Yangtze River has the highest sediment load. So regarding to the river morphology, the Yellow River and Nu Jiang River are kind of dominated by meandering river. All other 3 river types are dominated by braided or multi-thread rivers. So next, I want to briefly go through each one of the watershed to give you some visual tours about the river types in these areas. The first one is Upper Yellow River system, which is a very north watershed. As you can see, like this is on the left-hand side, the bottom, you see the longitude profile showing you the change of the slope of the main channel. The top one gives you the visual 3D representation of the watershed. On the right-hand side, you see the map showing you different types of rivers. So in this system, you see 3 types of rivers. Anna branching river, which is a pink line, mainly along the main channel, main Yellow River channel. Braided river is actually either along the main channel or in some areas like in the upstream section here and the downstream section here. And the meandering rivers is spread all over places. So next, I want to just give you some idea of each type of the rivers in this system. So now first, let's talk about the confined river systems. So this is what the confined river systems look like. The river morphology, the river is basically bounded by very high cliffs on both sides, meaning the shape, the size of the river is confined. The river cannot move freely laterally. And the second type is the braided river. And here is an example of the braided river in the upstream section. It's called the Dari Ridge. And as you can see in this one, the alluvial valley is relatively wide, and the bars between the channel branches is covered by vegetation. So this is a relatively stable braided river system. Next, I want to show you another very different braided river system in the downstream section called Daheba River. It's here. And in this river, you can see this is an upstream this is the upstream section of Daheba river system. As you can see, this river is it's a lack of vegetation. There is a rich sediment supply into this area, and that's mainly because the area was formed by the recent tectonic uplift movement. And the river basically cut into the geologically formed lacunar deposition, lake deposition, and which is why you see on the side of on both sides of the river, the soils are poorly sorted, and this is the middle section and the lower section of the river. So the main idea I want to point out is that the river has a very rich sediment supply, not only from upstream section, but also from from both sides. As you can see from the picture on the middle section, there are a lot of debris flows, hill slope collapse happening on both sides, provide rich sediment sources. The right-hand side picture shows you the downstream section of the river. It merges directly into here from the bottom of the picture, merges into the main Yellow River. Okay, so the last type of river in this system is meandering river. The meandering river is mainly focused in this area, which is called Zoic Basin, and this is the area we spend a lot of time because this is the area that has the world's largest concentrated area of alpine peatland. So let me show you some pictures about the meandering river in this area. So this is the meandering river in the very upstream part. As you can see, the river itself, the size is small, but if you look at the shape, the river is highly convoluted, showing the very high sinuosity in this area. And the green color you see here, most of them are actually peatland. This one is in the kind of in the middle of the watersheds. And as you can see, the river size becomes larger. And also the other feature you see is that there are a lot of oxbow lakes, right? And the biggest one is in front of you in this picture. So there are a lot of oxbow lakes formed in this area. It shows the interaction between floodplain and the river systems. The last one is the picture of meandering river in the very downstream section. And as you can see, because it's the mainstream, so the river size is big, and the size of the river bend is also very big. And you can see the asymmetric form of the river banks. The left-hand side bank is way higher than the right-hand side banks. So this is these are the three types of rivers in the Yellow River system. Next, let's go to Upper Yangtze River system. As you can see from here, in this system, there are two types of rivers, braided river and confined river. So I give you some sense of braided river because this river system starts from glacier area. So it's worth showing you some pictures about like a river in the south area. As you can see from here, it's a right start from glacier. Okay, and the glacier melting actually caused the retreat of this glacier, leaves a lot of space, as you can see from here, as additional sediment supply to rivers. And this is in the like a little bit downstream of the glacier. As you can see, sediment started to build up. The river sediment load started to increase. And when you go further down here, you see the valley becomes relatively wide, and as a result, the braided river structure becomes more and more complex. And this is another sub-watershed of within this area. As you can see from here, this is an amazing braided rivers in this section. The river valley is very wide. It's more than, I think, 3 kilometers. I mean, the width of the river valley. And this picture is taken by drone. And it just gives you an idea of how complex a braided river in this system. And the bottom one gives you like a close look vision of the river. You see typically the sediment bars developed in different areas. You can imagine during different storm event, the shape size of this sediment bars will change constantly. So in other words, the river is very dynamic. This is another part of this river system. Again, the river is river form is braided river. As you can see from this amazing picture on the right-hand side, the valley is the alluvial valley is very wide, which allows it to develop this kind of very complex braided river system. The red color basically tells you in the source area, the soil is from the rocks that contains rich iron. And when we go further down to the system, you can see this is a kind of confined river system. And again, this confined river system is a braided river system. We see it is confined because the width of the river system is bounded by the mountains on both sides, as you can see from both pictures. But the river itself is still very dynamic. From the bottom picture, you can see the sediment bars, very dynamic. So next, we go to the third system called Lancang River system. And in this system, I show you it's dominated by braided river system and confined river system. This is a braided river system in the upstream section. And as you can see, because it's upstream, so the river size is relatively small. But when we go further down to the middle part of the river, you see the valley becomes wider. So even though it is a confined river, but it's still a braided river and with very complex river morphology. And the next one is called the Nujiang River System, the fourth river system. And this is a relatively small river system. And what I showed you here is a braided river in a very upstream section. So the river system the size of system is relatively small because it's in the upstream section. When you go down to the middle and the downstream section of the mainstream, you see this is a confined river ridge. And again, you see the main feature is that the river is bounded or limited by the mountains on both sides. And it has no choice to move laterally. That's the key we can see from here. And also another thing is that we cannot see visually the slope of the river in this confined sections are typically steep. That's why we don't see a lot of sediment deposition inside the channels. The last one, which is on the very source, is called the Yalozangbu River System. And this system is, again, dominated by braided river system and confined river system with some meandering river system. I will give you just 2 examples. One is the so-called Lhasa River in the middle section of the main river system. Lhasa River is the main tributary joint into the Yalozangbu River. It is the river next to the capital of Tibetan autonomy called Lhasa City. And as you can see from this two pictures during dry season, wet season. The river system, again, is braided river system, but it is, again, very complex. And one thing you can see from this wet season is that there are obvious some areas, some patches with vegetation growth. And another example I want to give you is in the mainstream of Yalu Zambu River. From here, you can see the highlight point here is the regularly distributed vegetation, so which is created by artificial planting. So this shows you the human interaction in this river system. Okay, so at this point, I give you the base general description of walk you through all 5 river systems. Next, I want to briefly introduce you our studies, the work we have done in these systems. I classify our studies based on the river types, based on the number of channels. So I classify the studies into multi-thread river system and single-thread river system. So I started from a multi-thread river system. I realized that I have a lot to talk, so I have to be brief and leave you to ask me questions later. So the first study I want to introduce you is about the morphodynamics of of island systems in the Anna-branching ridge of the Upper Yellow River system, which is here. The first system I introduced you here. Along the mainstream here on the right, you see the red section. This is the part we are focusing on in this study. It is the Anna-branching river system. So we divided the ridge into 4 sections based on its morphological nature. And within each one, we actually got satellite images in these 5 years. And in each satellite image, we actually identified the islands, okay, not the bars. We identified islands, as you can see from the right bottom picture here. And then we actually studied the change of islands between the years. And based on the nature of the change of the bars, we classified the island dynamics into 6 classes, as you can see from here. I just want to focus on the 2. One is so-called island expansion, as you can see here. That basically means in the later image, you can see the island start to grow. And another one is called island shrink. And this is the opposite process. In later image, you see island start to shrink. Okay, what we discovered is that we over this like a 30-year time period, the island dynamics is mainly controlled by these 2 processes: island expansion, island shrink. And this is the table showing you the number of each type of the islands within this different time periods. And this figure, basically, I want you to focus on the highest bar, blue bar, which is expansion, the highest red bar, which is a shrink. So this basically allows us to conclude that the island dynamics is dominated by expansion and shrinking of islands. And by doing further studies about this bar island dynamics, we found that bar island dynamics can result in changes in Anna-branching numbers within a system through the repeated formation and elimination of small floodplain incised Anna-branches and minor morphological adjustment of main channels and the large Anna-branch. In other words, what we discovered is that the river system inside the Anna-branching system it is very dynamic. Small channels disappears, occurs constantly. Island increase, decrease constantly. However, the main branches and branches remains stable. This shows the signal that the whole branches system is essentially stable. So we think that actually means if there is additional sediment supply from the upstream due to whatever glacial retreat or the high rainfall event, the sediment that the part of sediment that cannot be transported through the system will be digested by the branching system, either by increasing island or by in the case of deposition, or by creating a new small branching channels in the case of erosion. And this way we call it digested. So the additional sediment of water will be digested by the system while the morphology of the system remains stable. That's the key I want you to remember. The second study I want to show you is this Yangtze River system. So the second river system. Here we select the two nested sub-watersheds. Okay, one is here, another is the entire watershed. So on the right-hand side, you see some like details of this braided river systems. What we do is that within each sub-watershed, we select the ridge in upper, middle, downstream section. We also select some ridges across the entire area, and then we measured their morphology, like breathing intensity and the total water channel width. We study their relationship. And here's what we got. So from this one, you can see this figure is concentration, suspended sediment concentration was precipitation. And the blue line is in the upstream sub-watershed, W1. W2 is the entire downstream one. So blue line is higher than the red line for a given precipitation. That basically means sediment supply in the source area is higher than the sediment supply in the middle downstream section. And what this shows you is the first two here, A and B, is essentially sediment rating curve. So in both what sub-watersheds, you see the sediment rating curve is very strong, which means that sediment transport is mainly controlled by flow, by water discharge, not by sediment supply or local erosion. And on the right-hand side, figure C shows you the concentration between the two sub-watersheds. They are very similar, which means across the system, concentration is similar. So that means the sediment, monthly average, the sediment remains similar across the system. The implication is that the increased sediment in the upstream part of the system has been transported through the entire system. So in other words, sediment transport in the whole system is balanced. There is no significant net deposition and erosion. Okay, now from the river morphologist side, here is the result. We show you the relationship between breathing intensity and the valley width. Solid line represent the wet season, dashed line represent the dry season. And you see for the ridge, the same ridge the ridge has a wider valley width, tend to have more branches of braided river during wet season than dry season. That basically implies that the morphology is more controlled by the flowing water, which is a discharge, or you can see precipitation event. This one shows you another evidence. Basically, the three figures on each row in each row shows you the morphological structures in upstream, middle streams, upstream, middle stream, and the downstream section of a sub-watershed. And you can see the shape of the change of breeding intensity is similar. And also in the other watershed, we see the similar shape of the morphological relationship. This basically says the morphological structure in two river watersheds remains similar. Again, that means the response of a river system to the sediment dynamics and the hydrological dynamics remains constant across the system. That's the take-home. That's the take-home message here. The other thing I want you to call your attention is that if you just look at the first half of this parabolic figures, you see actually there is a linear relationship between the breeding intensity and the value weights. I will get back to you next. So the third case study is about the Lantang River system, the third river system. As you can see, in this one, we choose the middle section of the river, and this is the focus of the study area. And we divided that into 5 small sections. These pictures are the drawn images we got. We divided the river we classified the river into 2 sections, two classes. One is the flowing water, which is represented by this blue color. Another is the red river, which is a dry river. It doesn't have water during the dry season. And this right-hand side picture shows you hydrological and climatic conditions. The bottom line here is precipitation. The solid line is discharge, and the dashed line is temperature. You can see temperature over past 30 years it started to increase, but both discharge and precipitation, oscillated, but with no trend. And this bottom one basically just show you over this 30 years period, hydrological regime remains similar, which means high flows occurs during summer and low flows occurs during winter. So what I showed you here is like the relationship between daily discharge and breeding intensity in this different years, and this linear relationship is another way mimic the parabolic structure I showed you just now in a different watershed. It indicates that different breeded river systems actually shows similar morphological structures, and this picture shows a very complex dynamic relationships of morphological structures. So I can briefly describe to you. So the top figure here shows the temporal trend of breeding intensity, which is normalized by discharge, and this way we can compare the images collected in different time when water discharge is at different levels. Overall, you see the breeding intensity start to decrease gradually over years. However, you see a lot of bump and up and down periods, right? In this, for example, in this area, you see up, you see 2 up section down and up again. And then in the next period, you see down again. So you see a lot of this up and down period. The bottom picture shows you the discharge. The orange color shows you peak discharge, and the other one shows you the number of days when discharge is higher than annual discharge. So the peak discharge actually in some areas the peak discharge its trend matches the trend of breeding intensity. This basically indicates that the activities is mainly affected by high flows. However, I used this example in 2016 7 to 8, which is here in this section, the trend of breathing intensity, the change of the trend of breathing intensity is opposite to the trend of the change of peak discharge. It basically tells you that the sediment supply in this period plays a role here. So if you put in this all together, what it shows, the take-home message is that breathing dynamics is very complex during different periods over the past 30 years. What I showed you here is that what we observed during this 30-year period is that all kinds of the morphodynamic processes that has been discovered in other river systems in the world are identified in this system. The first one shows you asymmetric bifurcation. The second one shows you avulsion process. The third one shows you extensive bank erosion. All of these can be identified from this system. So that tells you the morphodynamic processes in this breathing system is no different from the systems in other regions of the world. And this gives you again like another evidence for what I said just now. Because in this one, what I showed you is that this relationship, this black point is our ridge. The other data is from the breeded river systems in Europe, alpine areas. So you can see from both figures, the dotted either this black square or this triangle. These are our data. Our data blended into the trend of this alpine rivers very well. It indicates that our system is no different from the breeded river systems in Europe, alpine river system. So which is why we see here, we conclude morphodynamic processes in breeded river system are similar to those in other breeded river systems. The last one of breeded river system I show you is in Lhasa River, which is in Yajiang River system in the very south. And in this river, I really want to show you the human impact on river morphological structures. In this river, we select the river, the middle downstream of Lhasa River system, divided it into 4 segments, and we identified 4 types of human impact: farmland, afforestation, urban development, and sand pit. The 5th one is dam construction. Based on dam construction, we divided the study period into this 3 periods. P1, P2, P3 represent the different time periods for the 2 dam constructions. And then this one shows you the situation of urban expansion. As you can see, the urban expansion actually increased a lot in the 3rd section, reach C, which is this one, reach C. And the farmland decreases over time in all 4 reaches. And afforestation actually mainly happens in this reach A and reach B. So the idea is that human impacts shows spatial variations along this middle and downstream section. What I showed you here is hydrological regimes. Without getting details, I want to just say to you, the dam construction significantly changed the hydraulic regime. And here what I showed you is the morphological adjustment of the river's morphological segments. So this too shows you how the channel width changed. This shows you how the breathing intensity changed. Okay, they basically shows the decreasing over time, indicating the human activity caused both reduction of channel width and breeding intensity. And what's important is this diagram, the relationship between channel width and breeding intensity. Other than this point, all the points are basically falling along the same line, which basically means that morphological structure in these different sections under different types of human impact remains similar. That's the key. Even though human disturbance is intensive, but the morphological structure remains similar. That's the take-home message I want you to have. And in summary, for the breeded and upbranching river, we see like individual channels and bars, islands are very dynamic. It changes over time. However, the overall, the large-scale morphological structures remains similar. The localized changes in bars, islands, channels are digested or observed by the change of water surface areas or number of channels, the size of islands, but maintains the stability of morphological structure. And this discovery is against actually the popular ideas that is, I think, and that is prevailing in the scientific community. I show you these resources. When you have a time and place, take a look at this image, and they claim that breeded river in Jiang River system changes a lot, and I disagree with this idea. Next, I'm running out of time. I will quickly go through this meandering river system case studies. I'm sorry, it's 10 years of study, so it's a lot. So I try to be brief. So for the meandering river systems, we mainly focus on the Yangtze River, Yellow River, Upper Yellow River system, the first river system. And we focused on this area called the Zoic Basin, the area with the large concentration of peatland. And in this study, we try to study the lateral migration rate. We identified the bands along the two main rivers here. As you can see, the red color represents the two ridges. So we identified from these two rivers. We identified the two different types of band, compound band, as you can see from here, simple band, as you can see from here. We identified based on the migration of the bands. We identified the three types of movement: extension, translation, and the neck cutoff. And then we actually counted the number of each type of this. And then we studied the morphological characteristics of these bands collectively. So what we discovered here, I don't have time to go through the details of this. Just go through the two figures. If you see this figure, if you are familiar with the meandering river literature, you see this figure is very similar. So it basically says the band in meandering rivers, the band with the curvature between 2 and 3 has the highest migration rate. That's what this dashed line indicates. And our data actually confirms this. That means meandering river, the performance of meandering river in this area is not different from meandering river in other regions. And also we actually identified that actually the reason for the very tight band, the migration rate is low is because there are not many numbers of band that actually have very tight band. The band curvature actually focus on in the middle range of the curvature. For the very tight band or for the very broad band, the number of bands are relatively small. That's why it's actually the weighted migration rate for this type of band is relatively small. And the next, I go to the second study. This one is about bank erosion. So along the same area, we studied the river banks of this area. We identified that the bank basically experiences two types of erosion: fluvial erosion and bank collapse. As you can see, this is different. This is in different locations of the same river, Black River, and you see the banks. And in particular, in this one, you see the so-called cantilever bank. So the top part of the bank stick out. That is caused by the undercut erosion for the bottom part. So that's why we identified the fluvial erosion causing the undercut erosion, bank collapse, which caused the top part to collapse, forming complete this cycle of the bank erosion. We used this model to simulate bank erosion by simplify or prototype the banks we observed in the field into this theoretical structure, and then we modeled the processes. The key thing I want to emphasize here is that we, instead of different from the previous studies, when we do the model, we focus on the impact of hydrograph, which is one rainfall event, a series of flow, rather than one single flow. And we realized that in this study area, the peak discharge of a single or each hydrograph is closely related to the mean discharge. This gives us a tool that allows us to quantify a given peak, a given hydrograph, a group of discharge, that its impact using mean discharge or peak discharge. So here I want to go through this quickly. The top one basically just shows the so-called sediment rating curve, but the left-hand side is erosion rather than sediment load. And the left-hand side is mean discharge. So that basically means it's the effect of a hydrograph, a storm event, rather than single discharge. So this is the figure shows the relationship. The second one is actually here, it should be E sub C. It's a bank collapse relationship. So we developed the two so-called sediment rating curve. We say using this, we can quantify the impact of storm event on fluvial erosion, on bank collapse. And based on that, we developed the so-called effective discharge. This is again a classic concept in fluvial geomorphology. However, what we focused on, the unique part here, is that this is effective discharge based on hydrograph, not single individual discharge. This is the contribution of our work here. The take-home message is that based on our identified effective discharge, we realize that bank erosion needs to be caused by very high hydrographs, which means in this area, bank erosion rate is very low. That's the take-home message. And the other one is about bank erosion evolution. This one, the background of this one is up to now, all of the popular morphodynamic models scientists are using right now at this point, they are basically assume when the band width is narrowed down to the mean channel width, neck cutoff occurs. And this is the rule that has been used in all the morphodynamic models nowadays. What we discovered in this area is that actually there are a lot of bands we identified in this area its bandwidth, when it's less than the mean channel width, neck cutoff hasn't occurred yet. So we realize that this commonly used threshold standard is actually not right. And because of that, we studied this. So we picked up 14 bands in this area. And then for each one, if you look at this figure, for each one band, we identified historical images. We measured the band width. We also measured the mean channel width. And then we plotted the ratio of band width to the channel width against the time. These are each one of the figures in this picture you can see. And then we developed the equation, and then we use this equation to predict when neck cutoff would happen actually in these bands. So what we discovered is that it also, after the band width narrowed down to the one channel width, it still needs these bands to take about 52 to 161 years before the actual neck cutoff occurs. So what does that mean is that band evolution happens at a very low rate. That again matches what we discovered earlier. The last one I want to briefly go through is Oxbow Lake. It's basically about hydrological connectivity. I suspect that I don't have time to go through the details because I'm running out of the time. So I will skip the details of that. But all I want to say is that this study basically shows that I want to point out the 2 points. First, the degree of hydrological connectivity, which means the connection between main channels and the floodplain, such as Oxbow Lakes, the degree of connectivity is very low in this area. That's the 1 point I want you to take. Second, the process of Oxbow Lake sedimentation processes is similar to the sediment deposition processes in Oxbow Lakes of other regions in the world. Again, that means the Meander River processes here in this region is no different from the areas in other regions of the world. So putting this together, for meandering rivers in general, there are two types of rivers, meander rivers. One is the rivers located in the upper high elevation area where the area is dominated by permafrost river land. And the other type is the area dominated by the so-called seasonal frozen ground river systems. And these two systems have different characteristics, like in permafrost rivers should cut off dominated processes, but in the seasonal frozen ground areas, meander river is dominated by neck cut off. What it means is that overall in the Qinghai-Tibet Plateau for meander rivers, there is a so-called balanced change under the influence of global warming and intensified human disturbance. And for the permafrost rivers, sediment supply will continuously increase. It will cause more should cut off, such that meander river remains lower sinuosity. On the other hand, in the meander rivers in the low elevations, the migration rate remains slow, and morphological of the rivers is characterized by the very high sinuosity. So in conclusion, if you think about these two different types of rivers, in conclusion, here is what I can put up. First, the river system at a large scale is actually created by tectonic movement many years ago. It's stable. So it hasn't been changed over modern times. So that is the background of the river systems in this area. Second, the river morphology of all types, as I mentioned just now, they are controlled by the contemporary fluvial processes. And these fluvial processes, these fluvial processes are no different from the processes we observed in rivers in other areas, including in Amazon rivers. And the last one, the imbalanced hydrological cycle due to climate change in the Qinghai-Tibet Plateau will cause the imbalanced response of river morphology at the local scale. Now, keep in mind at the local scale, but at the larger scale, the river systems will remain stable. So put it in other words, the river systems, whether it's braided river, meandering river, and a branching river in the Qinghai-Tibet Plateau, will remain stable, even though the global warming will cause continuous glacier melting, permafrost thawing, and human activities will be intensified. But river system in the foreseeable future will remain stable. I stop here. I'm sorry, I'm a little bit over the time.
Thank you very much, Peng, for such a fascinating presentation. Time is not the problem. We are here to enjoy your experience and lessons on this particular area of the planet. Please, to the public, feel free to make questions. We have some interesting questions here, Peng. But first of all, I want to thank you because it's an incredible talk. We have been learning a lot about not only fluvial processes, because the amount of data and accumulated studies you have in this area with the colleagues of China, particularly Wuhan, is very, very impressive, with new discoveries, new perspectives on Bridle River. Bridle River have been always focused in, Canada, Southern Europe, and so on. So you are providing a huge amount of information from a very important part of the world. And in addition to that, for us in South America, you also, like a professor in geography, have been giving us a general picture of the geography, the characteristic of this peculiar region that our students are not familiar with. Let's start with some questions. I have the pleasure in having the participation today of Dr. Jorge Abad. Jorge Abad is a famous specialist in morphodynamics, and he's actively participating here today. Thank you, Jorge, for participating. I would like to include a couple of questions by Jorge, right? Luan, can you put the first one? So this is the first question by Jorge Abad. Is there any explanation behind the location where islands are expanding or shrinking inside of an branching structure?
Thank you. Very sharp question. The direct answer is no. And the reason is because our study is mainly based on morphological change over time, right? To answer the question, your question, we need to have the sediment transport data, sediment load data. We need to have a specific discharge data, like so, for example, daily discharge, such that we can actually link the location where island shrink or island expansion to the corresponding sediment load and water discharges. But because we don't have that kind of data, so we cannot directly answer this question. So, but this is a really good question, and you really picked up you get what I talked about. So I'm glad. This is a good question. But I want to say that to answer this question, we really need to have the sediment load data and the water discharge data.
Allow me to make a comment, Peng. And I think the interesting, I like the digestion concept, that you mentioned, it has to digest the sediment without changing too much the plant form. So we have a dynamic adjustment of the plant form, but we digest the sediment input that can be increased, but you not necessarily change the plant form style. That is what I understand about your explanation. And this is an interesting concept in terms of the resilience of these structures, ridges, the structure of these ridges. And of course, at some moment there has to be some threshold. We have this example here in the Araguaia, where we have been studying for many years. So the Ana branching structure was trying to digest the sediment because we have an incredible increase in the sediment load because of massive deforestation in the region. So we have this increase of sediment. So the system we're trying to digest it in the way that you mentioned. I like the concept. Was storing sediment in the Ana branching structures. You shown some simplification and changes in the secondary channels. We got the same. Finally, collapse in some way. So we arrived at a critical value where the system started to suffer some kind of metamorphosis, right? But it's interesting what you say, that it's not, we don't have to be just linear, like you showing your conclusion. Okay, we have this change, the river is going to do that, it's going to do that. No, depending where you are and the capacity of geomorphologic adjustment of each ridge, you can get different responses and not just the simple schematic response that people want to trigger all the time. You know, I modify the condition here and going to change the river that way. That you concluded that people was wrong about this kind of responses in some areas, right? We have more questions here. We have another question by Jorge Abad as well. You can read it, Peng.
Yeah, I'm reading that now. For the meander case, are you mentioning that peak discharge produces a high migration rate? Does the peak discharge include overbank flow or bank flow? Again, it is a very good question, and here's what I want to say. Our bank erosion modeling study basically indicates that, I mean, in general, if you think about the general morphodynamic processes, of course, higher discharge tend to cause a higher bank erosion rate, which tends to cause a high migration rate, right? But don't forget, peak discharge occurs with less frequency, which means for given time periods, you tend not to see peak discharge often. So this is the balance between frequency and the magnitude, right? High magnitude but low frequency, and that's exactly why we say, okay, we want to focus on the the collective effect of a group of discharges, not only by peak discharge, but also the high discharges close to the peak discharges, to see how do this collective discharge affect bank erosion. So that's what we're trying to do. We basically identify what our discovery is that, okay, you need even for the fluvial erosion means the river actually cut the lower part of the bank, erode the lower bank part of the bank. The discharge does not need very high. The medium discharge can reach that, can achieve that. So that's why fluvial erosion is more frequent, and our effective discharge for fluvial erosion is relatively low. It's definitely below the bank flow discharge. And the peak discharge you mentioned, you asked, actually that discharge is actually way higher than the bank flow discharge. Based on our study, bank flow discharge in that area is equivalent to discharge with the reoccurrence interval of 45 years. We only had that happen in 2000 2019 once. Okay, the discharge was about 45, the reoccurrence interval was 45 years. So this frequency of high peak discharge happens very low. As a result, bank rarely experienced effective erosion. Do you know? That's what I mean. I hope you understand what I mean here. It is rarely subjected to effective erosion. So collectively speaking, over a certain time period, the erosion rate is actually lower. That actually you can imagine in that area, the bank collapse, the frequency of bank collapse is actually lower. So that's what I want to emphasize here.
Okay, thank you very much, Peng. We have more questions. We have one by Deiser Sibaja. You can read it as well.
Okay. Similar relationships between braided channel and the queue over decades for the Lantang River can be found in other braided sections from other basins of the QTP. Yes. So this relationship, I assume you are talking about this parabolic relationship, the relationship between breeding intensity and how do I say, the main channel width. So that means when you have a when discharge increases, the total channel width increases. So breeding intensity tend to increase. But at a given level of discharge, breeding intensity reaches the top. When discharge further increases, actually some branches start to merge, and it causes the decrease of breeding intensity. That's why we have this parabolic relationship, right? So this is the process that we can think about, and this relationship, we not only identified this, saw that in Lantang River, which is the third large river system, but also in the second large river system, Yangtze River system. Actually, in two of our papers published about the braided rivers in Yangtze River system, we constantly see this similar relationship occurs. So basically that tells us like all the braided river systems in Yangtze River follows a similar morphodynamic structures.
Thank you, Peng. Thank you for your answer. We have more questions. We have now a question by Dr. Landerley Almeida Santos. Landerley is working in the China University of Geoscience in Wuhan. Welcome, Landerley, from the other part of the world. So let's move with your first question.
Okay.
You have the question.
So this question is asking me question of comparing Yangtze River against the Yellow River. So what you said, what controls the difference, right? Yangtze River is mainly controlled by, is dominated by the braided river, and the Yellow River is dominated by the mixture of meandering river and unbranching river. So meandering river has a more dominant role in Yellow River, right? You ask what's the difference? Why they're different, right? Here's my answer. For Yangtze River system, the main control is are the two things. First is sediment supply. Yangtze River system has a clearly higher degree of sediment supply. This is because of glacier retreat. significantly affected by constant, continuous climate change, global warming. And because the Yangtze River system, it derives from the glacial areas. So 30–40% of glacial areas in the exororic basins is focusing on the Yangtze River watershed. That's why it has, when glacier retreats, it creates additional sediment supplies to the system. The second one is the slope of river is generally steep in the Yangtze River system. That's again another reason why we have generally breeded river system. It's really, I'm surprised from very upstream section to the almost down to the outlet of the system, you see the breeded river distributed across the system. And I think these are the two main reasons. For the Yellow River system, we see the like a lot of areas is dominated by breeded river, meandering river systems. Why? I think that is because in the areas you see the meandering river is dominated. This is the area that has generally flat alluvial fans, and in these alluvial areas, the valley width is wide and the slope is gentle, such that it allows the river to move freely. Keep in mind, allows river to move freely. That is why in these areas you tend to see the development of meandering rivers. Another factor I want to point out is that in Yellow River system, along the main rivers, you actually, I don't know if you can see this. I'm trying to I'm trying to use the slides to show you my point. This is the Upper Yellow River system. Along the main rivers, you tend to see Anna Branch River and the Anna Branch River and the breeded river system along the main river. That is because along the main river, the channel slope tend to be steep, and also we tend to have a confined conditions along the main channel, because the main channel is formed by, we call the head cut processes over geological time periods. So this is, I think, the reasons why we see the two different river systems in these two large river system areas.
Thank you, Peng. And we have another one by Ladder Lake.
Okay, during high water stages, this river confine large areas of floodplain. When this happens, the old floodplain is essentially modified and subjected to new dynamic. So over high flow stage, as you see, this rivers confine large area of the flying plain. I assume this is about the meandering river system. Am I right? Can you confirm? I don't know.
I'm not sure. It's what specific kind of rivers. I think it was is related to, okay, so you have some lower terraces, old floodplain that are close to the active floodplain can be reactivated because you have been focusing on the channel dynamic, but maybe I think it is related because I know the kind of research that Lander Lake developed. Is you have the alluvial plain and you have reactivation of lower terraces. What is the relation along the different units of the floodplain with the channel dynamic?
Okay. For the breeded river system, right? I think your question is related to the I think the so-called connectivity, the connectivity between the floodplain and the rivers, right? For the braided rivers, this connectivity, the degree of connectivity is very high. And that is why we see, like in the Yangtze River, in the Lancang River, when I show the pictures of braided river, you see the braided river system is very dynamic. And this nature of dynamic is a signal showing the high interaction, the high connectivity between channels and its floodplain. In particular, if you recall, I showed you in the Yangtze River, like this Yangtze River. I want to show you this guy. Yeah, look at this guy and this guy. The floodplain is very wide. The floodplain is probably about more than 3 kilometers wide. It's very wide. Amazing if you were there. And when there is a high flow, you can imagine the flow is actually just overflow this area, extended into the both sides of valleys and working on the floodplain. And the result of that, it could create some smaller branches on the side of this existing braided river system. That's what I mean, the dynamics, the local changes of smaller branches of the rivers. And so, in other words, in braided river system, the connectivity, degree of connectivity is very high. In the meandering river system, on the other hand, in the Yellow River, there, the connectivity is very low, actually, because when you have the meander rivers like that, first, in these areas, the overbank flow happens rarely, which means the frequency of overflow is very, very low. As I said to you just now, the bank foot discharge is about has a frequency reoccurrence interval of 45 years. So think about that. It's the bank foot discharge is occurs almost 45 years or 50 years. So that means overbank flow happens rarely. That means the connectivity between floodplain and the channel, river channel, is very low. So this is what I want to say. For meandering rivers, it's very low.
Thank you very much, Peng. Well, I think we don't have more questions today. I want to thank you for this spectacular talk. I think that beyond all the fantastic results, they have been very motivational for all of us, also very didactic. It's a synthesis of a very long-term program in the Tibetan Plateau you have been developing with the colleagues. So thank you very much. And I would like to highlight also for the young participants here, your geographical and perspective about these problems. We more and more, every day we have more of these modeling issues, the gay guys doing modeling everywhere and trying to synthesize everything to some physical modeling or something like that with computers and so on, and lacking all the knowledge of the region they are studying, right? And having this general perspective of what are the factors that control the environment, why these factors interact and control the fluvial morphologies and fluvial dynamics, and that makes a big difference in your research. You know, I think this is a very important message for the young researchers. So I want to congratulate you about that, because our school is trying to do something similar, trying to highlight the importance of fieldwork, the importance of understanding nature like nature, and not just simplifying this like just a physical model or computational model going to solve everything. Right? Thank you very much for that. I would like to also thank to all the participants and the persons that have been raising very interesting questions here from all over the world. We have several international participants, as we mentioned before. I would like to say as well that we expect to continue our international seminars in 2026 next year. So we hope to have your participation, all of you, in the next year with exciting talks like we had today by Peng Gao. Thank you very much, Peng.
Thank you.
Well, that's all for today.
Thank you, Edgardo, for organizing this. I'm very glad I have a chance to present our results here. So thank you all for listening.
Thank you very much.